In this video, we are going to explain and analyze voltage in series and parallel circuits. So one possible analogy that can be used to help you understand and make predictions about voltages is the water model. So in the water model, we have a pump that would pump water, and as it pumps water, it would increase the gravitational potential energy of that water. As that water passes a turbine, that gravitational potential energy is then converted to a different form, or kinetic energy in this case. So the analogy can be made with circuits in that a battery would increase the electrical potential energy. And as you go across a resistor, this would convert the electrical potential energy to a different form, either heat or light. So I think that analogy can help with the conceptual understanding. Just a quick note, you'll notice here in a lot of these visuals and some of the sources you'll find online that there's positive charges that are flowing. And this is because when this was first being discovered, it was agreed upon to assign a positive charge as flowing through a circuit. We now know that the electrons, or we assign a negative charge to the electrons, are flowing in a circuit. It's not going to change any of our calculations whatsoever. This is called conventional current. When you have positive charge flowing, you'll notice in this simulation, we can change from conventional current to electron flow. It's going to change the direction of the current, but it's not going to change any of our calculations. So for the purposes of this video, we'll be sticking with electron flow. But just know when you see diagrams like this, that's what it's referring to. It's the positive charge carriers, or conventional current. So one more conceptual piece that we'll talk about now is the idea of a coulomb. So coulomb, rather than trying to measure the charge of individual electrons, which is an incredibly small charge, we group charges together in groups called a coulomb. So a coulomb is just a group of charge equal to the charge of that many electrons. So it's this massive amount of charge that it's easier for us to measure in. For example, if you want to measure distances from here to New York City, you're not going to be measuring in nanometers. You're going to try to measure in maybe kilometers or meters. So this just allows a better sense of scale with our measuring devices. So voltage, measured in volts using a voltmeter, is the difference in joules of energy for each coulomb of charge between two locations. This is also referred to as electrical potential difference. So let's try to explain that a little further. If we have a voltmeter, and our voltmeter measures 20 volts, this is measuring the difference in joules of energy per coulomb at two different locations. So here we go again with it. 20 volts, which is 20 joules per coulomb, is the difference between two locations. Or each coulomb of charge has a difference of 20 joules of energy between these two locations. Okay, so it's measuring the difference in energy, the difference in electrical potential between two different locations. So what does this look like? So if I have a voltmeter, and the voltmeter, we can set it up across the battery, and this measures 20 volts. So that means across here we have 20 volts, or each of our coulombs of charge, we can think of them as gaining 20 joules of energy as it goes across that battery. Now as we go along the wire, you'll notice that this is going to read 0. So why does this read 0? Well, remember, a voltmeter tells you the difference an electrical potential between 2 points. So the difference between these 2 points, I mean, using our water pump analogy, it's at the same height. There's no difference in gravitational potential energy. There's no difference in electrical potential energy between these 2 points. But if we were to go then across our light bulb, and notice I can put this really anywhere. So right now I'd be measuring this location and this location. We're noticing negative 20 volts. So it's a drop of negative 20 volts or a 20 joule difference for each coulomb. So what does this mean in series circuits? So remember our learning goal, we're trying to analyze and explain voltage in series and parallel. Let's first look at series. Here's various schematics of series circuits. If we take our voltmeter, let's go across our battery, we find 40 volts. Okay, so this gain right here is 40 volts. We're going to go across our first light bulb, and we notice, okay, with this light bulb, it has a 10 ohm resistance. So let's actually change that to a 30 ohm resistance. 30 ohm resistance, and we get, we change this just to match the schematics here. So again, across the battery, we have 40 volts. Across our first light bulb, we have negative 30 volts. Across our second light bulb, we have negative 10 volts. So what you'll notice is the voltage gained by the battery is the voltage lost across the resistors. So we can write this out in a statement where it's the voltage of the batteries for series. The voltage gained is equal to the addition of the voltages lost. For parallel, let's make sure that these are 30 ohms, 10 ohms, when we have 9 volts. Sure. So what we're measuring, if we measure across the battery again, so let me put this on one side, this on the other side, we measure this difference to be 9 volts. Now, what would we expect the potential drop to be across either of these two? Well, even though they're different resistances, and you can see even the two light bulbs are, one of them is quite a bit brighter than the other one, we're still going to expect to see that same potential drop across these two locations. So we have 9 volts. If we go down this way, we have negative 9 volts. And similarly, if we measure across this resistor, we also have a negative 9 volts. So what we have, a positive 9 volt gain across the battery, will have a negative 9 volt drop across each of the resistors. So they're all equal, at least the magnitude of these three are equal to one another. So in summary, we can summarize this using what's called Kirchhoff's loop law. So what we find is for a series circuit, so this is series, the voltage gained by the battery is equal to the sum of the voltages lost by the resistors. For a parallel, right, this voltage gain is equal to this voltage loss. This voltage gain is equal to this voltage loss. So we can summarize this whole statement in the sum of the voltages around any closed loop equals to 0. So if I have positive 4 volts, when I get back to my battery, I need to be at, if we're using our water pump analogy, we need to be at the same elevation at what we started with. And this can help us analyze and explain voltages in circuits. So this was our learning goal for today. Can I explain and analyze voltages in series and parallel circuits? Hopefully you can do that a little bit better now, and thanks for watching.